This section deals with matrices. A matrix is a rectangular array of numbers arranged in rows and columns and placed inside brackets. All the numbers that are inside the brackets are called elements. Here's an example of a matrix. So it's placed inside brackets and it has numbers arranged in rows and columns. Now we will be using matrices, and this is the plural of a matrix. So we're going to be using matrices to solve systems of linear equations. Let's first start talking about what an augmented matrix is. An augmented matrix is a matrix that is used to represent a system of linear equations. It has this vertical bar that separates the columns into two separate sections. The first group is going to be the coefficients of the variables in that linear system, and the second one is going to be for the answers. Please note, if you happen to have a missing variable, you have to put a 0 in for its coefficient. So when we are writing the augmented matrix of a linear system, you got to make sure that if there is no variable there, you write a 0 in for that variable. Let's practice rewriting linear systems as augmented matrices. Example 1 is 3x plus y minus z equals 9, negative x minus y plus 3z equals 3, and x plus 2y minus z equals 0. I want to write this as an augmented matrix. Well, first, I would draw those brackets. I'm also going to draw a vertical bar closer to the right bracket. Now I need to put in the coefficients of the variables on the left side of this vertical bar, and then the answers on the right side. So let's write the first equation, 3x plus y minus z equals 9. The coefficient of x is 3. The coefficient of y is 1. The coefficient of z here would be at negative 1. And then my answer is 9. So that represents that first linear equation. Let's do my next linear equation. I have a negative 1 for x, a negative 1 for y, a 3 for z, and a 3 for the answer. Finally, let's look at our last linear equation. We have 1 for x, 2 for y, negative 1 for z, and 0 for your answer. So this is the augmented matrix for this linear system. Let's do it again for example 2. We start off with those brackets, and then the vertical bar is going to go closer to the right bracket. Let's put this linear equation in. We have 1, negative 3, 2, and then the answer, negative 12. Let's do this second equation. Well, we don't have an x here, so I have to write a 0 for my x term. Y's coefficient is 1, z's coefficient is 4, and then the answer, negative 3. Last row, the last equation. I don't have an x term, nor do I have a y term, so I have to put zeros in for x, zeros in for y. The coefficient of z is 1, answer of 2. So the augmented matrix that represents the linear system for example 2 is 1, negative 3, 2, negative 12, 0, 1, 4, negative 3, and 0, 0, 1, 2. Again, everywhere we were missing a variable, we had to have a 0 placeholder. All right, let's do the very last one. Same thing, write the augmented matrix for the linear system in example 3. We open up our brackets. The vertical bar goes closer to the right side. For the first one, I have 3. I don't have a y, so I need a 0 placeholder for the y, negative 5, and then answer of negative 12. Second row, I don't have an x, so I need a 0 placeholder for x, then 4, negative 1, answer of 5. Last one, I have 2, negative 3. I don't have a z term, so I need a 0 placeholder, then the answer of negative 4. So the augmented matrix for the example 3 is at 3, 0, negative 5, negative 12, 0, 4, negative 1, 5, and 2, negative 3, 0, negative 4. Well, now we know how to write the augmented matrix of a linear system, and I said that we were going to use matrices to solve systems of linear equations. One method of doing this is to get that matrix into echelon form. What that means is you're going to have ones as your main diagonal going from the upper left to the lower right, and a bunch of zeros below those ones. So for example here, I have that main diagonal of ones, and then underneath each one of those ones I have zeros. So this is said to be in echelon form. Once we have our matrix in echelon form, we are going to use something called back substitution to solve the system, and we're going to get back to how to do back substitution soon. So again, in order to solve a linear system of equations by using a matrix, one method is to get it into echelon form. And again, that's a diagonal of ones going from upper left to lower right, and then zeros underneath the ones. Well, how would we do that? Because if you look at the three examples we had before, they didn't all have a diagonal of ones. Example 1 did not, and example 3 did not. Well, since all matrices don't always come in echelon form, we're going to use something called row operations to get into this format. Well, there's three different types of row operations. The first type of row operation is to interchange two rows. Interchange is another way of saying switch or swap. So for example, if I write this R1 and R3 and then the arrows pointing towards each other, this is telling me to switch rows 1 and 3. So if this is my augmented matrix, if I were switching row 1 and 3, well, since this is my row 3, it becomes my new row 1, and I write 1, 2, -1, 0. Row 2 stays the same because I didn't say I was going to do anything to row 2 when I did this row operation. And then this row 1 of my initial augmented matrix becomes my new third row. So I get -1, -1, 3, and 3 for my third row. A second row operation is that you can multiply a row by a non-zero number. For example, if I'm multiplying row 2 by 2, and it's going to become my new row 2, well, what I would do there is keep row 1 the same, because all I'm changing is row 2, but I'm going to multiply each one of these elements by 2. So I end up with 6, 36, -24, and 42. Row 3 stays the same because I didn't say I was going to do anything to row 3. So again, first row operation, you can interchange or swap two rows. Second row operation, you can multiply a row by a non-zero number. The third row operation that we're allowed to do is to multiply that row by a non-zero number and then add it to another row. So, for example, if I want to say 1/6 row 2 plus row 3, and then I'm telling you it's becoming my new row 3, well, what that means is for row 2, I'm multiplying each term by 1/6. And I'm going to do that on the side here, and then we'll write it up on the right-hand side. So 1/6 times 6, well, that's going to give me 1. 1/6 times 36 would give me 6. 1/6 times -24 would give me -4. And 1/6 times 42 would give me 7. So if I want to multiply row 2 by a sixth and add it to row 3, I would be adding this 1, 6, -4, and 7. Remember, this is a sixth of row 2 with row 3, and row 3 is -1, -1, 3, and 3. If I add those together, 1 plus a -1 is 0, 6 plus a -1 is 5, -4 plus 3, -1, 7 plus 3, 10. So this becomes my new row 3. So the matrix changes to, well, row 1 did not change. It stayed as 1, 2, -1, 0. I didn't change row 2 because the only row that I'm changing in the end is row 3. So I keep row 2 as 6, 36, -24, and 42. And my new row 3 is 0, 5, -1, and 10. So again, there's three row operations that we can do. We can swap two rows. So in this example, we swap two rows. We can multiply a row by a non-zero number. For example, here I multiplied the second row by a non-zero number. And the third row operation, we can multiply a row by a non-zero number and add it to a row. So I multiplied row 2 by a sixth and added it to row 3, and that became my new row 3. The row number on the end here lets us know which row is our new row. The next video we're going to talk about, well, how do we put this all together to actually use a matrix to solve a linear system of equations.